This looks like a harmless Arduino project, but hidden inside is a vulnerability that lets me completely expose the system. I'll show you exactly where this vulnerability is, how it can be attacked, and what you can do to stop it. To demonstrate this attack, I have built this simple Arduino LED controller. I press the button, the light turns on. I press it again, it turns off. If I had access to the underlying firmware on this device, I could change the circuit's behavior and even control it. By the end of this video, this Arduino will ignore its original firmware and run my malicious code instead. Most developers use the Arduino IDE to program their systems. The IDE is a fantastic tool which grants a lot of usability. However, the IDE abstracts away many things that can be useful for us. First, I'm going to investigate how the IDE actually communicates with the Arduino. Using this example, with my board connected, let's see what the IDE is actually doing when it compiles and uploads the firmware. Whoa, this gives us a lot of information. Some of it is useful. The IDE uses a package known as AVRDude to perform the firmware upload. Let's go to the terminal. From the man page, we can determine the exact command to run to achieve our goal. A lot of these items will not be relevant to us. We are just looking for the set of command options which let us read from the victim board. In our case, these options are as follows. -C. This option specifies the programmer we will be using to read the firmware. -b. This specifies the target board from which we will be reading. -P. This specifies the port on my desktop environment. -B. This is the baud rate. This specifies how quickly to send information to the target. -U specifies what the action is. In our case, we are going to be reading from flash. Using this command, we will attempt to read out the firmware from the board. And just like that, we've done it. Now, you may be wondering how I know that this is the correct firmware and not some random garbage. If we run a hex dump on the file, we will get something that is completely unreadable. Thankfully, in this environment, I happen to have the original firmware. I can tell the IDE to compile the firmware into a hex file and not upload it to the board. Now, we have the firmware saved to our machine. Back to the terminal. Now, if we do a hex dump of the file generated by the IDE, we will notice it looks a little bit different than the file we obtained from the programmer. This is because when we read from the flash memory, the programmer acquired all data in flash memory, which includes the bootloader and memory addresses that are not in use by our program. Our first step to compare is to remove the bootloader information from the file. To do this, we will first use a similar command to before. We will be using AVR object copy. This will convert our firmware hex file into a binary file, which will not contain memory addresses that are not in use by our program. We will run a similar command to the hex file generated by the IDE. Next step, we will remove the bootloader information from the extracted firmware file. The last step is to take a hash digest of our extracted firmware and our compiled firmware from the IDE. As these hash digests match, we can be confident that the data we extracted is the same as the data that was compiled. Therefore, the firmware we extracted is the same as the firmware that we compiled. Now, this exercise, while not related to our attack directly, does show us something critical about firmware integrity, and this is something we may be able to exploit further in the future. As good stewards of security research, The next question we should be asking ourselves is, how do we prevent this attack? Well, we can check the fuse pins to see if read protection is enabled. For that, we will need to read the ICSP pins, which are connected to the memory where the bootloader configuration fuses are held. We indirectly extracted this information earlier when reading off the full firmware from memory. Similar to our attack, we can execute AVRDUDE to read out all of the fuses, using this command. It has similar options to before, however, instead of reading from flash, we are reading off the fuse bits. So what does this output mean? Well, if we compare this output to the documentation on our target, the Arduino, we can see that this pin is associated with read protection. Of course, this is further evident by our attack. Since this pin is set to high, we can determine that read protection is not enabled. Of course, this is evident by our attack. To defend our system, we can set this pin to low to prevent firmware readout. This will prevent an attacker from exposing the firmware. I will not demonstrate that here, as setting fuse bits can potentially break the Arduino, rendering it e-waste. Before modifying any fuse bits, always back up your current settings to a safe location. If you are not careful, you might prevent the Arduino from receiving new firmware. Now, reading out firmware is bad enough for a system. Let's take this one step further. Let's see if we can upload malicious code to our victim. The Arduino IDE is freely available. Thus, to save time, I've written my malicious code here. For our system, I would like the LED to never turn off once turned on, which will require a full system power cycle each time to turn it off. In a real system, this could be catastrophic. For example, if this were part of a factory control system, power cycles could cause delays, costing time and money. As before, I will tell the IDE to compile the code and save it to a known location. This would simulate an attacker crafting a payload before delivery. Let's deliver the attack. Once again, we can use AVRDUDE, just like the IDE does, to send our malicious firmware to the target. The command is very similar to our readout attack, just with writing replacing reading. Alright? We have successfully uploaded our malicious firmware, completely replacing the existing legitimate firmware on the board. As before, when I press the button, the LED turns on. However, when I press it again, it remains on. Thus, our attack is successful. While this system is rather simple, the implications of such an attack are extensive. With increased system complexity, we may not even be able to detect malicious firmware during normal operations. Further, to prevent the board from being read out from or written to, fuse bits in the bootloader would need to be modified. This is a feature that has to be done manually by the developer. Otherwise, this attack vector will remain present. Most Arduino programmers will never interact with the AVRDUDE directly, as the Arduino IDE abstracts away many of the layers for usability. By peeling these layers back, we can expose capabilities not typically offered. This allows us to carry out much more meaningful attacks. Conversely, we can also be much more effective in our defenses. We may even be able to build a fully secure system without requiring end users to manually secure their device. We were able to complete our attack on a legitimate Arduino board. As Arduino is open source, there are many clones of this out there in the world. In the future, we will see if one of these clones is any more secure than the original.